All right. So in the end of the section in your book, they start showing you how Cauchy-Euler equations can be put into other forms by making certain substitutions. And your book actually talks about 3 different substitutions. I'm only going to cover one of those substitutions here, but be warned, you do have homework, I believe, homework problems on all 3 of them. And the reason I'm not showing all 3 types of substitutions here is because once you've seen one of them, the process for using the other 2 follows very similar steps. And I think it would be probably more instructive for you to kind of work through that on your own. But we're gonna just make note of something here. So first of all, suppose we have some Cauchy-Euler equation, and let's suppose that we've got some distinct real roots, m1 and m2, so that our general solution is going to look like c1 x to the m1 plus c2 x to the m2. Okay. Now this would be like case 1 of the 3 cases we looked at in the first video, but what we're doing here will actually work for all 3 of those cases. Okay, it's just easier to explain it with this. So I have exponential, or I have power functions here, x to the m1, x to the m2. I would like to try and represent these in terms of exponential functions somehow if I could. And you'll see why in a moment. So I can do that by rewriting these x to the m1, x to the m2 this way. Okay, c1 e to the m1 x natural log of x plus c2 e to the m2 natural log of x. And if you're not seeing why this is the same thing as this, remember your logarithm property allows me to take the m1, bring it up here as an exponent, so that becomes x to the m1 there. Same with the m2 here. And then the e and the natural log would cancel each other out, leaving me with that. So what I am doing here is I am setting myself up for a substitution. As long as x is greater than 0, and remember in these cases we are restricting our interval of validity to the positive real numbers, so this would have taken care of itself already, I can create a variable substitution. I can set t equal to the natural log of x, allowing me to rewrite this guy in the form y equals c1 e to the m1t plus c2 e to the m2t. This thing looks exactly like one of the types of solutions we would have gotten back in 4.3. In other words, this thing is the solution to a linear, homogeneous differential equation with constant coefficients, which we have lots of practice working with. So that would suggest then that if I made this substitution, if I set x equal to e to the power of t, and you made the appropriate substitutions in my dE, I can actually convert a Cauchy-Euler equation into a linear equation with constant coefficients, and then solve using the techniques we've already talked about. So I'm going to try an example where we do that. I think I have a bunch of blank pages here that I don't want. Put that there. Okay. So we're going to solve another Cauchy-Euler equation, but we're going to see about using this technique. Okay, here it is. Verify that it is Cauchy-Euler by looking at the powers of the x's and the derivatives on our y's. It is Cauchy-Euler. And what we want to do is make the following substitution. X equals e to the t. Now it's really, really important here that you remember that these y prime, y double prime, these derivatives here are all derivatives with respect to x. And we can't have that if we're making a substitution introducing a new variable t. We need them to be derivatives in terms, or with respect to t. So here's what I'm going to do. Let me rewrite the form of this thing for a second. X squared, I'm going to use Leibniz notation. Second derivative of y with respect to x minus 4x dy dx plus 6y equals a natural log of x squared. I want all of those x's to go away, and so here's what I'm going to do. First of all, if x is equal to e to the t, equivalently I could write that t equals the natural log of x. Okay, so that's going to be kind of important. Now, what I want to do is make substitutions for my dy dx and my second derivative of y with respect to x here. So in order to do that, what I'm going to do is use the chain rule. Okay, so here's one thing I know. dy dx, according to the chain rule, is the same thing as dy dt times dt dx. And if you're not used to seeing your chain rule in Leibniz notation, this is what it looks like, and it's important to know it in this form because it helps with these substitutions, okay? One of these two derivatives I can actually evaluate directly because I have t as a function of x already up here. So dt dx is just the derivative of this function with respect to x, which is 1 over x. That makes this thing the same thing as dy dt times 1 over x. Okay? Now, how do I find a second derivative? My second derivative of y. Well, that looks like this. Okay? But that's the same thing as differentiating the previous function up here with respect to x, which is it's the same thing as the whoops, didn't want to write that. Same thing as this. dy dt times 1 over x. Okay? Now, if I don't know what to do with this because I have a derivative with respect to t here, and I'm supposed to be differentiating it with respect to x, so that dy dt in there is not taking a form that I would like it to take. So I'm going to try and modify that. Actually, before I jump into that, let me just make sure I'm doing the right thing here. Oh yeah. So let's start by looking at what we're doing if this were like the product rule, because I have a product of two functions. Okay, so I'm looking at the derivative of the first function times my 1 over x plus the derivative of the second function, which would actually look like minus 1 over x squared times the first function, dy dt. Okay? Now, how do I evaluate this? Well, I can use the chain rule once again. So thinking of this in terms of the chain rule, let me kind of go up here to do this work. What is the derivative with respect to x of dy dt? Well, it's the derivative of y, the derivative of y, so it's going to look like this. Times dt dx. Okay? That's the chain rule where my first function was already a derivative, so I ended up with a second derivative here. But once again, we know dt dx, that's the same thing as this. Okay? So this guy right here is going to produce this term, second derivative of y with respect to t times 1 over x. This becomes, when I multiply it to that 1 over x right there, 1 over x squared times my second derivative of y with respect to t minus 1 over x squared times my first derivative of y with respect to t, or factoring that 1 over x squared out, I get this. That should be right there. Okay? The point of that is now, I know that was a lot of setup, but now what I can do is put in place of my dy dx and my second derivative of y with respect to x, expressions that only involve derivatives of y with respect to t. And then I have this factor, this term that still has an x in it here and here, but we're going to see those cancel themselves out. So taking these and plugging them into this dE up here, I'm going to get this, x squared times that second derivative, which looks like 1 over x squared, times second derivative of y with respect to t minus dy dt minus 4x times dy dx, but we're going to replace that with this guy, dy dt times 1 over x, and then I have plus 6y equals. Now the natural log of x squared, that's going to turn into the natural log of, remember, x becomes e to the t. Squaring that gives me e to the 2t. Notice the natural log and the e will cancel out, giving me a 2t there. So simplifying everything down, you're seeing the x squareds cancel here. You're seeing the x's cancel here. Everything is going to be in terms of t now. So now I'm going to get a second derivative of y with respect to t minus dy dt. And excuse me. And then over here, I'm going to have these x's cancel out, and I'm going to have a minus 4 dy dt. So that's going to combine to minus 5 dy dt. Then I have plus 6y, and that equals 2t. So this is, I know that took a lot of work to start with, but this is setting us up for what we were talking about before, because we've created a new differential equation in the variable t, where all of my coefficients are linear, are constants now, instead of functions of x or functions of t. I can solve this thing using whatever technique I like. So let's first find the complementary solution to this. My auxiliary equation is m squared minus 5m plus 6 equals 0, or m minus 2 times m minus 3 equals 0. And from that, I'm going to get the complementary solution, yc equals c1 e to the 2t. Remember, we're dealing with t's here, not x's. c2 e to the 3t. Okay, very quickly was able to get that. Now I'm gonna use undetermined coefficients to solve this guy, because we have a nice little linear function here. And remember, when this g of x over here is linear for yp, we assume this is going to have the form at plus b. I'm using the superposition approach instead of the annihilator approach, but that would have worked just fine as well. Yp prime would equal a, yp double prime is going to equal 0. Okay, I'm going to take these guys and put them up here. Now, even though I'm using prime notation, we are assuming that these things are derivatives with respect to t, because they're coming from this equation up here. So what does that lead to? Well, yp double prime is equal to 0. That gives me a 0 right here. Negative 5 times yp prime is going to look like negative 5a. And then plus 6y is going to look like plus 6 times at plus b. That equals 2t. Rearrange some of these coefficients here, or some of these terms. 6at plus 6b minus 5a equals 2t. Then we solve for our coefficients by equating them. So 6a should equal 2. That means a is going to equal 1/3. And then to solve for b, I would take 1/3, plug that in for a right there, and then I would use that to solve for b, which in this case, if you do the algebra, that's going to come out to 5/18 in the end. Okay? Now, what's left? We're basically done. We found our coefficients for our particular solution, and we had a complementary solution already. So let's put all of this together. My function, y, my solution is going to look like c1 e to the 2t plus c2 e to the 3t plus 1/3 t plus 5/18. Okay? However, we're not actually done yet, because everything is still in terms of t. Remember, t was a substitution that we made. Our original dE was given in terms of x. So we need to get this thing back in terms of x. It's not that difficult, though, because we have our relationship between x and t right here. So x is equal to e to the t. That means anywhere I see an e to the t showing up, I can replace that with an x. That's going to make this equal to, or y equals c1 x squared, since that's e to the t squared, or e to the 2t, plus c2 x cubed. T is the same thing as a natural log of x, so this becomes plus 1/3 natural log of x, and then a constant's not going to change, so I still get plus 5/18. Okay? So that's my solution. Again, I probably could have approached this without making any substitutions, but the idea here is to show how we can go back and forth between one type of equation to another using these substitutions. And we reduced a Cauchy-Euler equation down to a linear equation with constant coefficients, which again, we've had a lot of practice dealing with those. It allowed me to use undetermined coefficients on a problem where I wouldn't have been able to do that initially, okay? Like I mentioned before, I have a little note down here. There are two other substitutions that your book talks about in this section, but the approach is essentially the same as what we do here. You have to do kind of this preliminary work here, finding derivatives in terms of your new variable t, make all the substitutions, and then solve and substitute back at the very end. Okay? That's going to be it for Cauchy-Euler equations.